What are the best methods for oxidizing secondary alcohols to ketones? Owing to the good availability of secondary alcohols and the high synthetic versatility of ketones, this is an important chemical transformation, and many different methods have been reported. Those strategies suitable for the synthesis of aldehydes from primary alcohols have already been presented in other videos, and I won't discuss them here again. These are oxidations catalyzed by amine oxyls and oxidations with DMSO, iodoxyarenes, manganese dioxide, and chromium-6. All these methods are also well suited for the oxidation of secondary alcohols to ketones, which is much easier than the preparation of aldehydes. Ketones are much less reactive than aldehydes and secondary alcohols much stronger hydride donors than primary alcohols, and therefore a much broader range of reagents is available for the oxidation of secondary alcohols than for primary alcohols. I've split the subject into 4 parts. In this present first part, after a brief introduction, I'll show you the best ways to oxidize alcohols with hydrogen peroxide. Although some tricky side reactions may occur if too much oxidant is used, and some functional groups may not be compatible with hydrogen peroxide, this is one of the cleanest and least expensive ways to oxidize secondary alcohols. The second presentation will be about the use of hypochlorites as oxidants. In the third video, aerobic oxidations will be discussed, and in the fourth video, scope and limitations of the Oppenauer oxidation will be presented. Ketones are important synthetic intermediates and are prepared on a huge scale. Most prominent are acetone and cyclohexanone. Both are used as solvents and as synthetic intermediates. The global annual production of acetone is around 6 million tons and that of cyclohexanone around 4 million tons. Here I've sketched the most important industrial strategies for the preparation of cyclohexanone. Because of the huge scale at which these processes are run, most of these reactions do not generate any waste other than maybe dilute sulfuric acid, which can be neutralized and disposed of as calcium sulfate. One route is based on the hydrogenation of phenol, which can be prepared from benzene and propene by the so-called Hock process. Here acetone is formed as byproduct. Depending on the catalyst chosen, phenol can be hydrogenated either directly to cyclohexanone or to cyclohexanol, which can be dehydrogenated in the gas phase over copper or zinc catalysts. A mixture of cyclohexanol and cyclohexanone can also be obtained by the careful aerobic oxidation of cyclohexane, which is in turn prepared by hydrogenation of benzene. Cyclohexanol can also be prepared by hydration of cyclohexene, for which in recent years a route based on the partial hydrogenation of benzene has been developed, a quite remarkable feat. Usually, arenes are hydrogenated much more slowly than olefins or dienes, and no alkenes should accumulate during the hydrogenation of an arene. With a special catalyst, however, this partial hydrogenation of benzene became possible. An additional route to cyclohexanone is the oxidation and hydrolysis of cyclohexylamine, which can be prepared from nitrobenzene. Cyclohexanone is mainly used for the preparation of epsilon caprolactam by Beckmann rearrangement of its oxime and of adipic acid. Both products are important monomers for the preparation of various polymers. Besides their use as synthetic intermediates, ketones are also important target compounds for a number of non-chemical applications. Many products, such as paints, diverse coatings, and adhesives, require inexpensive, volatile, biodegradable, and non-toxic solvents, and ketones such as acetone, methyl ethyl ketone, and methyl isobutyl ketone are often used for this purpose. Some ketones are also important fragrances, for instance damascenone, camphor, or muscone. The conversion of secondary alcohols into ketones is a useful transformation because secondary alcohols are readily available and because ketones are valuable intermediates and target compounds. Secondary alcohols can be prepared by various carbon-carbon bond-forming reactions. The most flexible approach is the addition of carbon nucleophiles, for instance Grignard, organolithium and organozinc reagents, to aldehydes. Symmetric secondary alcohols result from the twofold addition of carbon nucleophiles to formic acid esters or to carbon monoxide. Secondary alcohols can also be prepared by hydration of alkenes and from epoxides. Finally, some alkyl groups can be either hydroxylated directly or halogenated and then converted into alcohols by nucleophilic substitution. Ketones are starting materials for several important C-C bond-forming reactions and can be transformed into a large number of other compounds. Carbon nucleophiles add to ketones to yield tertiary alcohols, olefins or epoxides. With cyanide, cyanohydrines can be prepared, and with ketones, beta-lactones may be obtained. Oxidation with peroxy acids can yield esters, and hydrogenation in the presence of amines is a powerful method for the alkylation of amines. Finally, ketone enolates can be alkylated or olefinated, giving rise to still further structural variations. Hydrogen peroxide is one of the preferred oxidants in the chemical industry because it is easy to handle safely, shows low toxicity, and only forms water as byproduct. For the oxidation of secondary alcohols, no noble metal catalysts are required, and the amount of oxidant can be dosed accurately. Moreover, in some of the reported procedures, no additional solvent is required. Main disadvantages of this strategy are the need of phase transfer catalysts for some starting alcohols and the formation of two phases in these instances. Biphasic reactions are generally less reproducible and more difficult to scale up than monophasic reactions. Furthermore, this strategy is not well suited for the preparation of aldehydes from primary alcohols because aldehydes are quickly oxidized to carboxylic acids under most of the reported conditions. Most transition metals will just decompose hydrogen peroxide into oxygen and water without oxidizing any organic compounds present in the reaction mixture. The few exceptions include tungstate, molybdate, and some rhenium, manganese, and iron complexes, which can activate hydrogen peroxide without catalyzing its unproductive decomposition. Only when activated by one of these few metal complexes will hydrogen peroxide oxidize secondary alcohols. One possible mechanism is the one sketched on this slide, in which hydride abstraction by a metal-coordinated peroxyl group occurs within a six-membered transition state. In this example, no additional solvent was used, but a phase transfer catalyst was required to provide for a thorough mixing of starting diol, oxidant, and catalyst. Interestingly, the primary hydroxyl group was not oxidized and didn't undergo elimination. In this second example, the same diol as in the previous example was oxidized, but instead of a phase transfer catalyst, a dipolar aprotic solvent, dimethylacetamide in this case, was used in combination with a phosphate buffer. Again, a clean oxidation of the secondary hydroxyl group took place. This example shows that phase transfer catalysts are not strictly required and may sometimes be replaced by a suitable solvent or solvent mixture. One potential side reaction of this oxidation strategy is the Baeyer-Villiger oxidation of the product to yield an ester. This reaction is usually mediated by peroxy acids, but procedures with hydrogen peroxide in the presence of various acidic catalysts have been reported. Therefore, no large excess of hydrogen peroxide should be used if ketones are the target compounds. A further problematic side reaction is the formation of hydroperoxides at reactive CH groups in the starting alcohol, such as tertiary, allylic or benzylic CH groups. Finally, Ketones readily form hemiacetals or cyclic acetals with hydrogen peroxide, so-called ketone peroxides. These are high boiling liquids or sometimes solids that can precipitate during workup or accumulate in distillation stills and cause explosions when heated or upon friction. Acetone peroxide has in fact often been used as nitro group free, difficult to detect explosive. So, one more reason for avoiding a large excess of hydrogen peroxide in this oxidation reaction. Here is a list with some more examples of different catalysts and reaction conditions. Closely related to the oxidation with hydrogen peroxide are oxidations with terz-butyl hydroperoxide or comyl hydroperoxide. These reagents are not as inexpensive as hydrogen peroxide, but show a better miscibility with lipophilic starting alcohols and may be a better choice in some instances.